Does anybody have any questions before I thought I would go over this memory management in a little more detail with you. But if anybody has any questions from the homework, we could do that first. I think the best question was, can we get if you don't mind sharing that make file with everyone else, that would be great. So they can see what it took. Mostly it looked like everything was just in the wrong place, right? It didn't take anything worse than that. Oh, there's a parameter in there that's the type of machine? Ah, 32-bit versus 64-bit. Okay. I didn't see that. That's probably why mine died. Okay, so what I thought I would talk about then is optimization techniques. How many of you have programmed for a Cray? Anybody? Derek has, I have. For those two of us, some of this will be familiar. There's some tricks that you do that are very non-intuitive that will change your performance by factors of 5. So you need to know about them. And that comes partway through. But in order to set the stage so that you'll see what that is, I thought we would go over memory in general. All right. So in general, when you're trying to switch your algorithm over for the GPU, you're turning what might be a serial code, and which is almost certainly a serial code at the loop level, into a parallel code. And so you want to, completely independently of the nature of whether it's a CUDA or Brooks or any other kind of parallel programming language, you want to maximize the independent parallelism. You don't want to have loop trips that depend one on the next one, because that's inherently serialized. For the GPU, and also those of you that have programmed for the gravity pipe, you want to maximize arithmetic intensity, which is to say, if you bring a number up from memory, you want to do as much with it as possible. Because the expensive thing is bandwidth to memory, and math is cheap. What that means is actually a complete change of focus. You may have done a lot of pre-computation in your current calculations where you even calculated some indices for later communication. You may have pre-calculated some floats or doubles and then imagine on your current machines, the table lookup is faster than recomputing these things, and that would particularly be true if they had square roots or trig functions or something like that. All of that is very different on this architecture. Trig functions, square roots, all of these are hardware accelerated, and the chip has an enormous number of integer registers to calculate things. So it's usually better to recompute things over and over and over than it is to try to cache it or to pre-compute and save it in a lookup table. And that's a very different strategy than you might be used to. In other words, the GPU puts all of its transistors on the arithmetic units, not on memory, relatively speaking. And then I already told you this twice. Do more computation on the GPU. Don't move the data back and forth. So transforming back and forth. So for example, let's do the limit of that, which is, as Bullet says. Let's say that you have some particularly non-parallel, clearly serial, forked, branched, complicated bit of coding that you think, really, I have to do this part back on the CPU. If it involves moving a bunch of data and then coming back, bringing the data back to the GPU, let the GPU run it in serial, because the communication time will kill you. Even if it's not elegant, it's going to be a lot faster. Okay, one of the things that we'll talk about a fair bit today is coalesced versus non-coalesced memory. That changes the performance by an order of magnitude. And the issues that we're going to talk about primarily are in the global memory. It was the example that I gave you that we talked about, and I put into notes on the matrix multiply, but I've got another example today, and just a simpler one for transposing a matrix, so that maybe it brings out the issues more clearly. In shared memory, there's something called bank conflicts, and this is something that's extremely familiar to the Cray programmers, all three of us in the room. Bank conflicts are mysterious and strange, and they work directly against you if you have a spectral code. Because in spectral codes, you typically have things that are powers of 2 in size, and the shared memory really hates things that are powers of 2 in size, because there are 16 memory banks per memory element. And if you want to access memory that's strided by 16s, you'll end up with conflicts. I'll show you what that means. So it's a strange thing. Okay, shared memory is small. It's a group of threads can share memory together, but it's hundreds of times faster than global memory. So you really want to learn to use the shared memory. This allows you to do some synchronizing of activity among threads so that your code will start to look a little bit like the MPI code that you may already have written, where there's blocks to prevent race conditions, or semaphores sent one processor to another that say, I've completed some part of the calculation, now you can go on. You can do that in groups of threads, which is to say within a kernel, but not across threads. So I'll show you an example of that. You also want to, this happens under the hood, but you have to organize your loops correctly for this to work. And that is, you want to use just 1 or 2 threads to go and get something from main memory and then share with the other processors. And it can be default. If you've declared the variable shared, then the other threads will have access to it, and then you synchronize after you've read, and everybody will be in good shape. So consciously using a few threads to go and get data is better. And then this is the most important thing too. We want to use shared memory to avoid non-coalesced access to global memory. And I'll give you a long example on that. Okay, that's the real hands-on for today. Whether you're using a GPU or any other parallel computer, you want to use parallelism effectively. So you want to partition your computation to keep the graphics processors, multiprocessors, all equally busy. Typically what this means is, you remember that there's a certain number of threads that are grouped together. 16 in the current generation of technology are grouped together in what's called a half warp, and then 2 half warps make a warp. There's several warps on a block, and then the blocks are that's like your loop variable. You loop over blocks, and the processors will hide all the latency of their work. If a block stops because it's all the threads are off getting something from memory, it'll just bring another block in and work on that until the stuff comes in from memory. So you want to have lots of blocks and lots of threads. On the other hand, you want to keep resource usage low enough that you can have lots of blocks per multiprocessor, and this works against you, so there's the balance for the optimization. The more you want to use shared memory, the fewer blocks you can run at the same time, and so that's the balance. Otherwise, you would just use a zillion blocks and all the shared memory you wanted. So that's the overview. That's what we're going to talk about now, some details. For the specific chips, here's what, and Friday you'll see a lecture on another specific chip, the Cell Broadband Engine, which is a different graphics processor. These are the Teslas from NVIDIA. They have 240 scalar processor cores. Each, typically, you can think of as executing a thread in the kernel. They're grouped into 30 streaming. They're grouped into 30 groups of 8 streaming multiprocessors. They each have 8 scalar processors, 1 double precision, 2 special function units. That's like the trig and the square roots. And they have shared memory. So here, if we break one of these little guys out, there's 8 scalar processors, a double precision unit. There's also these special functions, which are not shown in this cartoon, and then there's shared memory. So this is the unit of processing that you can synchronize over. So you can, all of these guys are going to share the memory down here. So trying to pull together the picture in your mind between hardware and software, it looks like this. In software, you think there's a thread of the computation. One trip through the kernel for the given thread index tells you what's going to happen on that trip. Threads are grouped into blocks, and the blocks are grouped into grids. In hardware, there are these scalar processors. Well, it is true that threads are executed by scalar processors, and thread blocks are executed on these multiprocessors. I told you 2 lectures ago that you shouldn't count on a block running on the same multiprocessor. I subsequently have learned they're not migrating them, but I have heard talks from the CUDA engineers where they say they can freely move them around. At any rate, the thread blocks are not migrating, but you might have several of these thread blocks running on a single multiprocessor, and in fact, that's the limit you want to be in. You'd like to have many blocks per multiprocessor. So if you go back, if there's 30 of these multiprocessors on a single GPU, you want to have chunks of computation large enough that you can have more than 30 blocks, and preferably large multiple, like 240 blocks or 270 blocks or much, much larger of threads, so that when any individual group of threads comes to an instruction which takes more than 1 clock cycle, or more than n clock cycles, where n is a small number, the multiprocessor will switch that one out and bring the other thread in to work on it until it gets to a point where it has to wait on some part of the calculation. And what's nice about these machines is they're very, very efficient in switching between blocks. What that means, though, is that the resources available to a group of blocks are limited by the total amount of resources on a given multiprocessor. So there's a constraint. That's what I was talking about. There's only so many registered for temporary variables or shared memory and things like that. We'll come back in a minute. So the grids then are many blocks. If you have many grids, that comprises a kernel. So you launch your kernel as a grid of thread blocks, and only one kernel executes on a GPU at a time. So that's the hierarchy of all this crazy language. And there's more. There's warps. So let's talk about that. Within a thread block, there's many warps. This number has been changing very rapidly as the chips evolve in time. So you should not latch on and say that 32 or actually 32 threads per warp has been changing, but the number of warps per thread block has been changing. So a thread block is a group of these 32 thread warps, all running on a single multiprocessor. The half warps, so half of these 32 thread groups, can coordinate global memory and access in a single transaction, and that's coalesced reads, which I'll talk about a little bit more. Okay? So it's kind of dizzying to keep all this stuff straight. Here's what it looks like to you when this is a good picture to have in your mind. Here's your host computer sitting over here. This is what you normally program for, the CPU, and you have your RAM sitting nearby in the computer. The chipset, which is what we always call the video controller, or the GPU, has on it its own DRAM, which is effectively broken into local, global, constant, and texture. It's mostly global. And this memory is available to be seen on the GPU. Different multiprocessors, all of them can see the global, and then groups can see these other ways. We'll talk about this in more detail in a minute. I'll come back to this picture if you have a question. Here's kind of scoped out for you. I had this chart in a previous talk as well. Okay, so here's the 6 kinds of memory. The first is called register memory. This is on the GPU chip. It is read-write, one thread at a time, has access to that piece of information. And it lives as long as the thread lives. So if you have a kernel, the kernel is launched and there's a thread that does its operation. When that, let's say the operation is nothing more than add 2 plus 3 and save it. location in memory. As soon as that's done, that thread is gone, and the register information is lost. Local is somewhere else. It's not on the GPU chip. And it is otherwise similar. We'll come back to the local. Actually, I'm confused why this says off-chip. I would assume that is on-chip. I'll check that for you. The shared is on-chip and is available to all the threads in a block. And the example that I'm going to give you in a moment has this written out carefully. The other three are visible from the CPU, so you can do things to them from the CPU. And these include global, which is the basic memory, constant, which is read-only, and texture, which is read-only but has the special application that you can read off, interpolate either linearly, bilinearly, or with cubic splines, all on the fly. Or maybe it's just trilinearly. I have to check. I've only used the bilinear texture myself. Okay, so let's look at how we would optimize given that hardware layout. So data transfers between the host and the device. Here's some sample numbers for bandwidth so that you can get it a good map in your mind. From the GPU to the CPU, the bandwidth is much lower than anywhere on the GPU to anywhere else on the GPU. Okay? This does not mean from one GPU to another. This means intra-GPU, so within one graphics processing unit. So, for example, if you have a PCI Express for the fabric of your parallel computer, and then you can get 8 gigabytes per second peak throughput from the GPU to the CPU and vice versa. Whereas if you're on chip or on device, you can get 141 gigabytes per second. So you really, what is that? That's a factor of 18 or something? You really don't want to go to host unless you have to. So that means you want to minimize transfers. Oftentimes it's best to allocate, operate, and deallocate on memory without ever bringing it back to the host memory. And all the examples I showed you in Flagon were that way. The data is allocated on the GPU, filled with zeros, operated on, and then finally we get whatever number we want from the computation and bring only that part back. And then group transfers, very important. If you can organize things so that you go and get one call for memory, and it's a large contiguous chunk of the memory, it's much better than many small ones. Because the compiler can optimize that. Had a friend do that once with a cereal bowl. It's really funny to watch because, you can see it getting out of control. The amplitude gets bigger and then smash! Oh, well. This one still works. Good. Now, this is something if you're OpenMP. Have any of you ever run an OpenMP? Nobody? Just have to look up from Facebook. Okay, so OpenMP is a... So let's remember, here's the story. Let's say that Peter and I are GPUs, and someone over here is a CPU that's my host, and someone over there is his host. If he wants to give me a piece of information, first, he has the data on his GPU, he hands it to his CPU, who hands it over to another CPU and hands it to me. If that's the way, that's conceptually how two GPUs can talk to each other, okay? Now, you can do it. Let's say that, in fact, there was only one CPU controlling the two of us. If it were MPI, so that there were two independent message passing interface threads or processes running on the CPU, one of them controlling him and one of them controlling me, the way that it works, if he wants to pass memory information to me, is it goes to his MPI process running on the chip, which then copies the data to another array on that chip and then passes it to me, so there's a copy. Okay? If you can take advantage of the information on this page and pin the host memory, it simply means that the two different processes on the same CPU can both see the same memory, so it doesn't ever have to be copied. And similarly, the GPU always knows where it is, so it accelerates the process of going and getting memory, because you don't have to calculate where it is in memory. So there's special ways to do what are called page lock data transfers. I have not done this. There's examples in the CUDA SDK for bandwidth tests, and you can play around with this. It's relatively specialized. It's not the center of what I wanted to tell you about. Okay, this is more important. You can overlap the motion of data and some of the computation. So you can have two different kinds of ways of thinking about this. There's asynchronous and stream APIs. And these allow you to overlap the data transfers from the, let me get this right, from the host, from the CPU to the GPU and vice versa. And it works like this. I mean, it's just what you think. If I know I've got to go get some piece of information for the next stage of the calculation that's going to start when I finish the next loop, I can go ahead and call for that, and while that's being brought over, I can finish the loop I'm on, and then when I get to the next loop, it'll already be there. Some of that happens behind your back by the compiler optimizing, hiding latency, but you can make it happen if you can explicitly tell the compiler that there's an opportunity to fetch data before you need it, then it's better. Now the way these two work, if we think of the asynchronous, well, let's do the stream. Let me show you the example, and then we'll come back and look at a definition. So asynchronous data transfers is exactly what you would think. You just simply say, time to copy something from memory in an asynchronous fashion. This uses that pinned host memory. And then while that's happening, I can go off and execute a kernel. So here's a memory copy asynchronously, executing a kernel, and then here's the CPU function, the next one that I want to call. So these things happen, in particular this, is happening at the same time as the CPU function. Now, to understand this, we need to know what a stream is. So now we'll go back. So a stream is a sequence of operations that's all executing in order in a GPU. And you might think, oh, that's my program. But it doesn't have to be that way. Your program is a parallel computation, and it can divide into many streams of computation. Each of one has to follow, which is full of instructions which have to follow one another. But there's many, many such streams which can all be done in parallel, right? So a stream is any such sequence of operations. And if I can explicitly label parts of my calculation as stream 1, stream 2, stream 3, and tell the compiler ahead of time that stream 1 is independent, what happens to the data in stream 1 over this section of code is independent of the calculation I'm going to do on stream 2 over here, then the compiler can take advantage of that. So there's these stream IDs which you use to do that. Asynchronous data transfers only work with stream 0 down here, or at least that's the default, and this is the more interesting way to do it. More interesting is to use non-zero streams. So the idea is you want to, if your computer is up to date, there's something called CUDA device properties, which is a function you can call on your laptop to find out what are the properties available to you in the GPU that you have in your laptop. Or more generically, you can write your code so that it queries, if you've got a GPU available to you, it'll query and say, you know, what properties does it have? And it'll return in an organized fashion and tell you whether, for example, device overlap is enabled or not, which these things will, in my experience, it's about 9 months where there's different chips out there with different capabilities, and then they're only producing chips with the new ones. and about a year later, everybody only has the new chips. So this is just a way to manage different levels of graphics cards. Okay, so the kernel and the transfer then, the kernel which you can do independently of the data, so you're going to do some calculation, and while you're doing that calculation, you can bring over some data for the next calculation. If you know that's going to happen, then you can use different streams. You can label the calculation on the data you already have in hand as stream 1, label the operation of going and getting the new data as stream 2, and then the compiler knows that it can parallelize over that. And so stream 0 is special in that anything that calls a stream 0 blocks everybody else and can't be overlapped. So here's the example. You can create a stream 1, you can create a stream 2. The asynchronous call memory copy would be stream 1, and the kernel would be declared in stream 2, and then those can go on at the same time. Okay? So such things can be done. Synchronization. There's contextual or stream-based synchronization. Let's look at contextual. Here you can call thread synchronize, which will block. It tells everybody to wait until all the previously issued CUDA calls from that thread are complete. So this is sort of like a barrier in MPI. Stream-based is different. This is like a barrier where your communicators or your handles are not, what is it called, world? I forgot the standard name. You know, in MPI, what's the communicator for everything? Yeah, MPI COM world. So here these streams are like the communicator for subsections. Okay, and so you can synchronize only the guys that have that common handle. And then you can also find out whether a stream is running right now, and you can, and this is really very handy because you can find out, is that stream running, has it completed, has it set a flag, and that doesn't get in the way of the thing actually running. So on the stream-based way, let's say we were going to do some all-to-all communication. Typically, you have to watch for race conditions. I'm going to do prepare some data in a buffer, and then I'm going to send that buffer over to someone else. I want to make sure that the buffer is filled before I try to send it. Well, it's also the case that the processor where it's going to be sent has to be told that it's coming, and so he needs to wait until the non-local event of filling the buffer has happened before he tries to execute receive for that one. So you can look for events. So I could, in my example, the first processor could set a flag that says I have loaded the buffer. You know, put a 1 in some array, and that is visible to other streams running in the calculation. So you can send signals across streams, and the event is recorded whenever the GPU reaches it in a stream. So this is just really useful. And then you can have a process wait until that event has been recorded by another stream in the calculation. All right, I'll leave you that for your notes. All of this is on the wiki. Okay. So there's also a way to do things accessing host memory directly, and this still involves hundreds of cycles of time, so this is not quite as powerful as you might think it is, but there's no copy statement. Okay, so I would have, there's no one in here with one exception who has been doing lots of CUDA programming, I would not try this optimization until you've got a code working which has the explicit copy the data here, copy the data there, this stream is independent of that stream. Get that stuff working. Then you can, if you've pinned the memory, as we talked about before, you can actually have the operation automatically, if I need a variable, I can tag that piece of memory so that it will go and get it. It's just as expensive, and there's really, I don't know any real value to this. It just simplifies the coding a little bit. So here's some thinking about it. What they're doing is planning for the future. So AMD bought ATI, and they're going to release chips where the CPU and the GPU are much more closely integrated on one die, perhaps. And if in that future, zero copy will be great because the data, the implicit call to off-chip memory will actually be an implicit call to on-chip memory, and life will be good. It'll be faster in some other examples, but it's complicated, and so I wouldn't go into it unless you're thinking of the future. And so in this context, I leave this in for you, but I wouldn't go there. Let's see how the optimizations actually work and how you can measure them, what kind of considerations there are. Okay, one thing that comes up in meetings is what is a theoretical bandwidth. So the clock speed might be 1.1 gigahertz. The memory interface, how many bytes at a time I'm going to go get. It's DDR memory, so I have two streams. And then this denominator is, you know, if we're thinking honest gigabytes, it's 1,024 cubed. If we prefer to think of 10 to the 9, then some people will put a 10 to the 9 in the denominator. When you're comparing your performance versus someone else, some published performance, these little differences actually matter. And so you just want to be consistent. Either use 10 to the 9 bytes in a gigabyte or 1024 cubed. It makes a difference. So for example, they say that they get 141 gigabytes per second on a Tesla, and you get one, and you do some simple test, and you can never get more than 132 gigabytes per second. It's because they used a billion rather than 1,024 cubed. The effective bandwidth is just defined to be what you would do for copying an array of these things. Nothing funny about that. Okay, so given that, let's look at the main topic of this. This is the most interesting part of the presentation today. So, again, this is familiar to people who had to think about memory back on the vector machine. So global memory access of 32, 64, 128-bit words is tricky if it's not aligned. You've all used -d align or something like that in your compilation. And so you know that these things happen even on the current chips. Most of it today is done by the compiler, so you haven't had to think about it. But here we have the complication that if I say go get something from memory and I have a block that's launched with 16, let's say it has 16 threads in it or 32 threads in it, those threads, each one is going to go get one element of memory. Okay, so I've launched a whole bunch of people to go to main memory at once and ask for data. If they're all asking for the same piece of data, the machine is smart enough to make one copy and broadcast it to them, and life is good. But if you ask for any other pattern other than each one asking for a unique individual piece of data, you get into trouble. And on the older devices, which you may come across in your laptop or in older machines, if the data is not aligned properly in memory, so that I'll show you a picture in just a second, you'll find that things slow down in crazy ways. Okay, so here's an example. Global memory here is, here's a 128-byte segment, two 64-byte segments, four 32-byte segments, and here comes 16 threads which are going to read the memory. Okay, so you have a simple thing which says B of I equals C of I, and C of I is in memory, so it's going to go and find them. Okay. With CUDA 1.0 and 1.1, which most of you will not have to deal with, but some of these laptops will have it, the kth thread has to access the kth word in the segment. We'll do the paren in a minute. And not all threads need to participate. But this is extraordinarily fast, and this was 16 times slower. So look closely. What it meant was each thread had to be in order, asking for the next place in linear memory, no matter how the 3D array was saved. Looking in linear memory, it had to be in order. It was okay to skip as long as that thread also skipped that point in memory, so you didn't have to do things. This was very tricky to manage, and if you had one crossing, then you just had to go 16 times and ask. Similarly, if it wasn't aligned, that was 16 different transactions instead of just one kerchunk and all of memory came in, okay? Things have gotten much better. Most of you have this capability, which is the one that you need to think about. So this is still one transaction because I think that arrow should be coming over here. We'll go over the details in a second. I believe it's only 1 to 1. So this, I got a goof. This arrow should be pointing at that element. So this is one transaction, even if they're permuted in any 1-to-1 fashion, is what I meant to draw here. Okay? It's 2 transactions if they're misaligned by 1. So the 64 and 32-bit byte, alignment is here. So if the variables were misaligned, instead of this being 16 transactions, it's now only 2. So it will go and get 1 and then pick up it'll get 15 and then pick up the 1. And on the 128-byte segment, it doesn't matter if it's misaligned, it will get them all in 1. So it knows how to offset from the start of a misaligned variable. This just means that things work better for you without much thought. You don't have to manage where the data is specifically with the newer capabilities. But if you don't ask for data in such a way that the points that are being requested are contiguous, then it slows down quite a bit. And that's non-coalesced reads and writes. Okay, so some coalescing examples. We'll look at the effective bandwidth of some small kernels that are copying data and see what happens with offset and stride. We'll take 2 GPUs, an old FX 5600, which you might have. This is not that old. This has the 1.0 and a peak bandwidth of 77 gigabytes per second. And the newer GT6, most of the Apples, I think, in the room, GTX would have something, I don't know. Does anybody know? Have you looked on your Apple? Is this a crazy number? This might just be the Tesla, I'm not sure. There's 1,000 model numbers. Anyway, if you've got the new compute capability, the modern, or the 6-month, 9-month-old one, we'll compare those two things. Okay, so this is global. That means it can be issued from the host. And all we're going to do here is copy output data from input data. So this is just C of I equals B of I. But the integers are going to be offset a bit, okay? So all this does is we find the block and thread indices, and then we goof up by adding 1. Let's look at the old one first. If you were offset by 1, you immediately drop down a factor of 16. So you didn't want to be offset by 1. The loss on the copy with the offset on the newer ones looks like it's just as big a drop, but this is now only a factor. This is a much smaller factor, right, in terms of overall slowdown, because it's going to compute the offset in only 2 trips rather than 16. This is not a factor of 16 drop. This is, instead of reading them all at once, you take 2 trips to read it. So this is only a factor of 2 hit, okay? What about striding? This is the most common thing you'll run into because you have some 2D data and you want to pick off the Y direction. So you're striding across some array, and here output, we're just copying input to output, and now they're striding. So we look at every 1, 2, 3, 4 data elements. So we're offsetting them, and you get a real precipitous collapse in performance because now this stuff is coming, it's not coalesced, it's not adjacent to each other in memory, even on the newer chips. So you don't want to do this. This is very, very common in these multidimensional problems that most of us are interested in, Typically, the stride would be the number of grid points in some direction, so it's not 18, it may be 1,024. So very large strides, which means you're nailed down here at a very low effective bandwidth because of non-coalesced memory. This can be fixed, and here we're going to do an example like the matrix-matrix multiply. This can be fixed by using shared memory to tile the problems up. So let's look at how that would work. Shared memory. Shared memory is a lot faster than global memory. You can think of it as managing cache. Threads can cooperate through shared memory, and the fundamental thing you're trying to think of is avoiding these non-contiguous read and write to global memory. Okay, so the examples are all going to be of the nature, read in a little bit more data, share it, and then write it back out in a different order than I would have written it, so that it's written out in an order which is again contiguous. Okay, so I have an example. Before that, we have to see how the threads actually look at the memory elements in shared memory. So the way shared memory is set up, there's a chunk of memory, a memory cell, whatever this thing is called, and there's 16 banks in the memory. There's lots of different threads accessing the memory, and all 16 of these banks can talk at once in one clock cycle if things are done right, and that's what you want to do. So each bank can service, that's what I just said, they can all service an address at the same time, but if you screw things up, it'll slow down and be 16 times slower. So how does it work? Multiple simultaneous accesses to a bank will result in bank conflict. This was familiar to those of you on the Cray. So typically, back in the old Cray days, if you had 512 by 512 MHD simulation, it ran significantly faster, factors of 3 faster, if you made one of the indices 513, the dimension of the array 513 rather than 512, because that changed the pattern of memory reading and writing. Same thing happens on these devices. What I've never understood is why they don't make 17 banks or something instead of, it would just make our lives much, much easier. Okay, so here's an example. You have your 16 threads. This is, of course, the easy one. Everybody's asking for one piece of information from memory, and each of the 16 bank elements can go and get their piece of memory, so everything is good. This is with a stride of 1. Again, a random one-to-one permutation, so that if this guy's asking that bank and this guy's asking that bank, it doesn't matter. As long as everybody's asking for an independent piece of information from memory, in shared memory, that won't slow down. Here's where things get bad. If I have linear addressing with a stride of 2, thread 0 might want something from bank 0, then thread 1 wants to jump up to bank 2, thread 2 to 4, 3 to 6, and by the time you get down to the bottom 8 members of the thread, this guy goes back to thread 0, and thread 9 is again bank 0, thread 9 is again going to bank 2, and now this is going to slow down. This is a two-way bank conflict. Each bank is being asked by 2 different threads, so this goes twice as slow. Here, you can slow down by a factor of 8 if the stride is 8, because of the mod of the banks. The first guy goes here, the thread 1 goes all the way to 8, thread 2 comes back to bank 0, so this gets really horrible. Again, if you had 16, it's smart enough to decode 16 for you, and it will just do a single broadcast. But anything less, and it freaks out and slows down dramatically. Okay. So shared memory is stupendo fast if there are no bank conflicts. And there's some profiler signals that we've not talked about that can help you decode this stuff. But here's the 2 examples. If all the 16 threads are accessing different banks, everything is fine. If all of the 16 threads read the same address in memory, everything is fine. It's smart enough to go get the thing once and broadcast to the group of threads. Okay? What's slow is if multiple threads of the group of 16 are accessing the same, any of the same banks. And that will serialize the accesses and cost you, as I described before. So you want to avoid that, okay? So what do we have in mind right now? We have global memory, which we'd like to read in order. And then we have shared memory, which as long as we're accessing the memory, the shared memory, in a way that each thread is looking at a unique piece of memory, we'll be able to go fast. So here's this transpose example. We want to transpose this matrix and turn it into this one. So this chunk comes over here. Okay? So the elements, and let's say that 16 thread, let's say that this is a 4x4 block of the matrix. And we have 16 threads. Each one is going to get one little piece of data and move it over to one little piece of data in global memory. Extremely simple thing to write. That's the trivial thing you would write would do this. And I have code. So here's the basic code. It basically says we calculate we calculate the index in and the index out. For the data coming in, they're in order. Turns out the order is it's going to read all of the lines here, reads all the rows first. So these guys are in row order, and so it's a coalesced read. But when it writes it out, it's striding by 4 in the example I said, if it's a 4x4 tile. But it's striding by the width, whatever the width is of this tile. Okay? So, so that's going to give you bank conflicts. Actually, sorry. That's going to give you non-coalesced write. There's no shared memory here. That's not bank conflicts. That's going to give you a non-coalesced write because I'm now writing information into O data, and these are not next to each other in memory. Okay, so if we want to pull it together with shared memory, what we want to do is access the columns of the tile while they're in shared memory and then write those out as rows, and everything will be great. Okay? In order to do that, we have to make sure that the groups of threads are synchronized so that everybody's loaded at the right moment. Let's look at how it goes. Again, in the I data, I'm going to read in a line. Okay? Now this tile, the whole thing is stored in shared memory. Okay? So now I've got all 16 threads have gone off and found each of their pieces of information from memory. That was 4 coalesced reads, the way I'm describing it. Now, when I want to write out this line here, I can read the data that's going to go into this line, I can read from this tile. And so it's reading it in a different order than I read it. It's writing it in a different order than I read it. And I can just do that as follows. So these examples are loaded on the wiki for you. It's a little bit more complicated, but it's not that bad. And basically what we have is the same kind of transpose, y to x. We calculate the out index, and we have this tile. So once we've got the whole tile read in, right? So we have, everybody goes and gets their I data, copies it into this tile. We synchronize, and then we write it out in a different order. And this is now coalesced. So it sounds complicated, but if you study these examples, it won't be bad. The problem is you can still run into bank conflicts, so you may try that example. Depending on the size of the calculation you do, you say it doesn't speed anything up at all. This sucks. Probably what's going on is bank conflicts. So if you have a 16 by 16 shared memory of floats, then the data in all of these columns are in the same bank. And that's going to give you really, 16 way is actually okay. So this is the trick that I mentioned to you before. If you declare your shared memory, if you've got powers of 2 here for your tile dimensions, you don't want to declare the shared memory that way. It's just a silly trick. You just make one a little bit larger, and now if you think about how the data is in memory, it's staggered by just the right amount so that the reads, I don't have a picture, so that the reads from here will turn into writes, which are all in a line without bank conflicts. Okay. Last thing, textures. This is a way to get data out. It's terrifically valuable for a lot of the codes that we've been talking about. The data is cached, so you read it once and then you've got it available. You've got linear, bilinear, and trilinear interpolation that's done in hardware, so very, very fast interpolation. It knows how to do the boundary conditions. At least it can do modulo for you. So it'll if you're doing a doubly periodic domain, square domain, and you're doing a simulation in that domain, it will do all the mods and all the finding of the indices for you, which is great. And let's say your box is 128 grid points across, but it's 7 units in whatever problem you're doing. You can ask for the 126th element, or you can ask for the value of the array at the X location, say, of 6.3827 or something, and it will interpolate automatically for you. So you can just directly ask for the data in the actual physical variable that you're interested in. I'll show you that. So integer or normalized coordinates. So it's pretty cool. Here's the texture, and you can either ask for the 1-1 element, or you can ask for stuff in between. You can ask in non-integer coordinates that are just the bin number of the data, or if this in your code goes from 0 to 2 pi, you can ask for pi over 3 and get the information at the appropriate point. It knows how to do all that for you. And then it does the mods, or it can just find the edge for you in the way that you would expect. So this is extremely good, and it does it very quickly. There's some detail here, which I'm going to more or less leave out, except down here, by the time you get into the most modern CUDA, you can declare an area of global memory to be texture for the purposes of part of your calculation. Then you can read out whatever you want with this kind of indexing. Everybody can read it once, so it's very fast. It's limited to 2D, and so you can either read by the float or the integer addressing. You can just trying to think. I'll come back to that in a minute. And you can have the boundary conditions in different ways. I'm just realizing that the example that my student did may have hidden something from me. Perhaps you can't go 0 to pi. She may have been filtering that back to the integers. I have to check. But anyway, you can definitely say you want the 2.5 grid point or the 2.3 grid point, and it will find it. She may have had a loop in there. Say it again. Do I need to worry about running over? So do you mean if I had 128 grid points and I asked for the 129th one? Is that what you're asking?
Not really. Say your texture is like a few thousand.
Yeah.
Now you want a few thousand points.
Yeah. Okay.
The one each one.
I don't understand. I don't know. Oh, round off error. Oh, yeah, it's not IEEE compliant, the texture. So it's a little bit, it loses, I can't remember what they said. You lose a couple of digits compared to full IEEE compliant. Well, what I mean is the number you get out. The way I understood the discussion was, I've got an array of floats, and I ask for something in between the grid. The number that I get out is not, the address, I believe, is good, but the number that I'm pulling out is not IEEE compliant to the full digits. Okay? And the more I think about it, the more I think this was hidden. So, but anyway, float or integer addressing. Okay, so this is just how to do it. We don't need to go through this right now, but basically, you can, on the fly, you can declare something to be texture, use it in that advantageous way and then release it back to be regular memory. So it's just a useful thing to know that you can do. This is an example. Here we're just doing it with integer reads, and down here, got this example. I don't even know. But the fundamental point is the copy with the shift continues to work quite well, and now we can be off grid as well. Shift can be a non-integer, although in these examples, this is an integer. All right. I put lots of stuff up from the NVIDIA engineers. You want to write your code as efficiently as possible, meaning as parallel as possible, with coalesced memory read and write. You can use these little tricks of fixing stride problems to take advantage of shared memory to fix those things. I have examples loaded up for you where we use textures. I didn't put any examples of constant memory, but that's pretty straightforward. And this bank conflict stuff usually comes down to not accessing things in patterns of 16. So as long as you don't organize your data that way, you'll be fine. Okay. Any questions? So I have a question for you. How many of you have done parallel computing, period? Okay, almost everybody. Is anybody planning, I mean, you know, you're here, but what is the planning cycle? Do you want to use GPUs in the near future, long term? Just holler out, near or long. Yeah, well, so actually, you know, you may have noticed that I don't know this stuff as well as I should. I have the advantage of having a student I can lock in a room and make Kate do it. But still, I think it's short term. What would make the distinction? I just want to see what you're thinking. What would be the distinction between short and long term for you? What kind of problem would you do in the short run? What in the long?
We're going to do analysis in the short run using CUDA on large data sets.
So like just transforms then and things like that?
I did some for calculating boundedness, but we're going to move like projections to data sets.
Mm-hmm. Okay, so that in that circumstance, you can do it all on one GPU because you just bring the stuff into memory, calculate, and be done. The long term, if you were thinking short term for a multi-graphics processor application, I think you made a mistake. It's possible to make that work. We put information online where you can get access, free access to this large cluster of Teslas so that you could try that out. But the communication patterns from GPU to GPU, unless you have an embarrassingly parallel calculation, are very slow. And so I would put off trying to do a strongly coupled, highly communicating calculation on a batch of GPUs. What other kinds of things are people thinking? We have 2 more minutes. I'm just curious.
If I could get gadget running on the GPU, you said.
Okay, so you're going to share your make file. And Peter, while you were out, we paid off the fellow who figured out how to compile. And he's going to give you the make file that we can put it on the wiki. It's run so far on a Dell and a Sun, but not on an Apple. It hasn't been tried on an Apple. It might just run on an Apple.
So my question is, with that, will we be able to do large simulations with something like Gadget in the near future? Because right now you're going to be limited by the memory on the GPUs.
Right, and it depends. Everybody here has got a different computer.
Right.
If you had a Tesla...
Even if you had a Tesla, could you do something that can be done on like a modern supercomputer?
No, but you could do something that could be done on a modern 4 gigabyte. So the Teslas are going to have order 4 gigabytes of memory. And so you could do something that you'd fit on a serial processor, and it would run a lot faster. It's hard. Parallelizing it is where the cutting edge is, the bleeding edge, whatever you want to call it. Any more comments?
What's the limit on 2D spectral codes right now?
Size?
Yeah.
depends on how many fields and what algorithm you have. We've been experimenting with that a little bit. I found it surprisingly low, and we're trying to track down what the problem is. We were trying to do, so for FFTs, if I just wanted to do FFTs, I could do pretty large 2D FFTs. But when I wanted to push forward a set of fluid equations, let's say, on a 2D grid, the number of fields that I have depends on the how deep is the time stepping algorithm and how many fields. For a modest algorithm that only had, I think, 14 total copies, 14 2D arrays of that size plus some temporaries, we were having trouble going above 2,000 squared or 1,000 squared. It was really quite silly. I think, and I didn't understand that. I thought we should be able to do much larger. If you just add up the numbers, it seems like you should be able to do more. No, that was with, so we're in this stupid situation of having like 5 different models because we've been playing with it for a couple of years. And actually some of our own test results get confused because the student will have used a GPU that they thought they were using a different one. So you need to be careful. If you're just starting out on this, it's worth trying to make them all the same model just for the purposes of timing and performance and size. Anything else? What else is on your minds? This is the last time we're going to talk about this here in any sort of organized way, so if there's anything you want to get off your chest. Okay, let's get coffee then.